Hello and welcome. My name is Kasim Loan and I'm a senior data scientist at Johnson Labs and the CTO of Dijkstra Labs. And I've been working in big data and data science for almost 10 years now. And today I will show you how you can leverage in just one line of code over 200 state-of-the-art biomedical NLP models for over 50 domains, which we will cover all today. So, to first understand, in case you don't know what is Spark NLP and Johnson Labs, we just do a quick 30-second recap because it's relevant to know. So what's Spark NLP? Spark NLP and the healthcare version of it provide all of the models and the software we use. And Spark NLP is basically a big data library for the NLP domain, focusing on being the most accurate, fastest and scalable model library out there. And it has accumulated millions of downloads in only a few years since its inception. And by now, it has become the most widely used NLP library in the industry and used by many honorable customers and awarded by the industry with various awards for excellent work. And if you look at all the features and all the models, you really see why. Spark NLP and nowadays also the NLU library has all of the features you could wish for. And in over 4,000 models in over 200 languages. And with NLU in just one line of code. But you might already know this. We've done a couple of webinars for that. Today we will attack the healthcare domain with NLU. And I will show you how you can use any of the 200 healthcare models for the roughly 50 domains of healthcare problems. And I will explain them all to you and show them to you with concrete examples. We will do a quick recap of how to use NLU, which is basically just two methods you need to know and maybe a third one. And after that, we go over all the algorithms in the medical library of Spark NLP and NLU, basically, which will be the named entity recognizer, the assertion models, the de-identification, resolution, and relation. And for all of them, we cover all of the problems code attack. So, just a quick overview and cheat sheet. Here are almost all of the features Spark NLP for healthcare and NLU offer for you. On the one side, you can get all of the medical terminologies like SNOMED, CPT, UMLS, and so on, and extract named entities from dozens of domains, and of course, get the relationship between individual entities and assert the status and of course extract them. And so, how would you use this with NLU? How do you get all of this magic, all of this power? It's very simple. You just need to know there's an NLU.load method, and in it you put the name of the model. Or nowadays we like to call the name of the model a spell, because it's like magic. Okay, so you put the spell name or model name in the load, and it will return to you a model object. And this model object has a predict method. It can take in a pandas data frame or all the Pythonic data structures, or even simple strings. And so in a concrete example, you would say NLU.load emotion, and then you have the model object, and with the model you can say model.predict INO of NLU. And this gets you a pandas data frame. Which one? Exactly this. So if you type NLU.load emotion.predict INO of NLU in just one line, you get this data frame with deep learning sentence embeddings, the category of the sentence, which will be predicted. In this case, it's an emotional classifier, either as surprise, sadness, joy, or fear. And in this case, it's a joyful sentence. So it has the category of joy, and we have also all the other confidences here. Cool. So that's already everything you need to know, right? There's NLU load and model predict. That's it. And then maybe I will show you there's model.viz for visualization, but that's all. So now we covered the NLU basics, and now we can go into the meaty stuff. The overview of all of the NER domains we have in John Snow Labs. So for the NER, basically, I created this table structure and nice overview for all the domains. And you can see here quickly on the first glimpse, the first column tells you what's the domain. So in the first case is an adverse event model, or there are multiple even of them. And you have here a description. So this finds adverse events between drug entities and problems. And you can get it with the NLU Streamlit NER.ArtBiobird, right? That's just the model name. And some entities that can be extracted would be aspirin or vomiting, and they would be predicted as drug and other. And in the very last column, you always have the reference links to the dataset or paper and all relevant links. And so we will use all of them in the notebook, which we come to in a second, but just so you understand the structure because of this table, because we will see it a lot. And then now on the first glimpse, we already see, we can get adverse drug events, anatomy, molecular entities, chemical data, drug data, posology, risk factors, cancer, disease data, clinical admission data, and much, much more. And maybe also interesting is the protected healthcare information, which is relevant for the de-anonymization. And there are so many domains that there's even a second page, the second slide for even more NER domains, where there's like the general one and the radiology and a couple more. But this was it for the medical NER domains. We will see them in action in just a second. But now we come to the assertion model domains. And if you're not familiar with these algorithms, don't worry, I will explain them in detail when we are at the code. Now you just get these slides as a quick reference. So for the assertion, you can assert for there's either the radiology domain, so you can assert the status of radiology entity, and I will elaborate what that exactly means in a bit. And also on the other side, the healthcare entities. You can assert the status of a healthcare entity, and there are basically 3 flavors, but they're basically pretty much the same, give or take class. And then one of the very interesting and powerful algorithms are the resolution algorithms or models. They basically take as input an entity and give as output and a code or a label, right? And this is very relevant if you feed these resolvers diseases or problems, because there are many medical coding standards defined that can give you an ID for all your diseases. And so in concrete examples, we have the ICD-10 CM or the PCS version, the ICD-O, the HCC is for the billing, and the first 3 are for diseases basically, and oncology, and we go into them in a bit again. And we have basically CPT, which is again for problems basically, the LOINC, HPO, UMLS, SNOMED, and even what you can get is the RXNORM of all your drugs, and the normalized version and the code of the drug. And finally, the most complex and advanced algorithm and domain we offer are the relationship domains. And relation basically means that for every entity, right, if you have a sentence with multiple entities, each pair of entity can be in some relationship. And this relationship we can try to extract and predict with the relationship extractor models. And some of the domains, at the beginning it might sound confusing, but if we go to the examples, it makes all sense. We can basically get a relationship between dates and clinical entities, or body parts and directions, or body parts and concrete problems, or body parts and procedures, and adverse events basically, phenotypes, temporal events, tests and results together with dates, and then of course also clinical problems, and then the more complex relationships, which have basically many classes, are like DDI for drug interactions, posology, and also chemical interactions, which are defined in 10 classes basically. Cool. And yes, since the relation table is so big, it's actually again split up in 2 sides. You have here the first overview, and then on the second side you have actually all the examples, which I encourage you to take a closer look in detail after this webinar. But we will go also into these examples now, more in detail. So now it's time for the coding. So what you do is you open a new tab and you Google NLU John Snow Labs GitHub. And if Google is good, yeah, it gets the typo. And we basically go to the John Snow Labs NLU GitHub page, right? That's the GitHub page of NLU. We click on, all we do today will be in the examples folder, and there is a webinar folder, and in there is the healthcare webinar folder, and here is everything we will be doing today. The NLU Healthcare webinar, the Jupyter Notebook. So this one mighty notebook, how do you open it? You just click here and open it, and this one notebook will cover everything we do today. This table is not properly rendered, but we will see it again in a second. But basically, what we have here, on the side you have a very nice table of contents, right? You can always open and close it, which can be very helpful with a very large notebook like this. Oops, let me leave it open. And basically, in the beginning here, we have first of all the overview of all NER models, which I just mentioned. So I just scroll over this, right? These are all the NER models, all the assertion models with nice explanation, and we come to this again in a second. The resolution models and the relation extraction models with a nice explanation. Cool. But now we want to actually get started with coding and get the super basics with NLU going, and then play with the healthcare domains. So to get started with NLU, all you need to do is hit this play button and install NLU. But I already did that, so I will close this, but what you would do is run this, and I already prepared the same notebook here for us, and it's already warm and has NLU installed for us. So I imagine now you already installed this, and now what is the next step? It would be that you run this cell. And if you run this cell, since we are using licensed code and licensed features in NLU, you need a Spark NLP for healthcare license. Usually you should have been emailed one via email. You should have this JSON file, and you just upload it here. You click on choose file and upload the JSON file, and that's all you need to do. Okay? If for some reason you don't want to do this or cannot do this, you can also manually enter all your secrets. You can open the file or check your email and enter them all here and uncomment this. And then run nlu.out or read the docs. But this is basically how you would set up the authorization. If you upload the file, NLU will automatically detect it, and now we can have some fun. And so, as a super basic intro or example, I have here a very standard NER. And I can now run this again, but it makes pretty much sense. And I won't be running most of the code today because there's a lot of code and we don't have so much time. But I have everything pre-cached. And basically, what are we doing here? We are loading an NER model, NER pipe, into this NER pipe variable. It's the model. And it has a predict method, as we've seen on the slides. And I am predicting on the entities, Peter loves to visit Berlin. And this takes now a second. But while this takes a second, we can already look at the next code. Where we see once the NER pipe is done, we can call an additional method, the viz method. And with the viz method, we can basically visualize the output of almost any model in NLU. And in this case, we can visualize the named entity labels. So in this case, the model predicts for Peter that it is a person and Berlin is a GPE. In this case, GPE means country. And so, and also maybe to get a rough high-level idea of what's the named entity when this is computing, we could maybe skim this intro. So what is maybe a named entity? In general, named entities, right? They are substrings in your text data, which can be classified as some class. So you could have the text Tesla is a great stock to invest in, and then Tesla is a named entity, and it's of type company. right? And that's already it. So it's basically find segments in your text that belong to a specific class. And here in the NER overview, you see in this sample entities, these are the text you give it, this piece of text, and in the labels, it's the class that's predicted, right? And we now will go over all these classes. Cool. And then now going back here, cool, now it's already also done. So what happened now, once we run the computation, we, as I mentioned on the slides, we get a pandas data frame, and it gives us one row per detected entity. So the first one is Peter, and it's of class person, and we have the confidence and also word embeddings for it. And then of course we have Berlin, and it's of type GPE. And then of course we can visualize it. And it's all we need to know today, right? Everything we will be using, now we will repeat this pattern all the time. We will NLU.load a model, we will predict one time, we call this. These are the 3 steps we now will repeat 50 times. Okay, this is all you need to remember. And then you only need to know what are the spells, the model names. Okay, cool. So let's get started with the medical domains. So the first medical domain we can use are genes and phenotypes. Phenotypes, if you are not familiar with the term, are basically observable physical properties of an organism, right? Like blue hairs or bleeding from the ear also. So basically things you can observe. And so here is a concrete example. How first of all do you load this model? You just say met.ner.humanphenotype.gene.bioword, and this gives you now again the model. And with it you can predict on the string. In this case we say the APOC4 expression in the patient shows poly something and poly something and some other thing. And basically we can see the first term, APOC4 is a gene, polyhamadonis is a HP. HP means phenotype, and polyuria is also HP, and the last term is also 1. And then of course, instead of looking at the table, which is eye straining, we can now just also look at the visualization right away, and then we see, okay, right, we confirm APOC is a gene, that other thing, the other 3 terms are HP entities. Perfect. And now that's all you need to know to scan and search all your data for HP and gene entities. Boom, that's it. Next domain is the adverse drug events domain. What's an adverse drug event? Adverse usually means a bad effect of taking a drug. And so one example could be, and so what are first of all the entities? We can get drug or other for the adverse effect, and we could say patient reports when taking aspirin, he experiences nose bleeding. But when using paracetamol, no bleeding from nose. And then we can look again straight. Now we can just go to the visualization. We don't need to look at the table because we can go faster, I think, a little bit. And we can see that aspirin is a drug and nose bleeding is an adverse drug event. And we also see paracetamol is a drug, but no bleeding from nose is not an adverse event because no bad effect, right? That's not an event. So we properly extracted the adverse effects and can distinguish from actual effects and not actual adverse effects. Perfect. Then the next domain, which will come later very in handy for the relation extraction, is the anatomy NER, which lets you find all the mentionings of anatomical parts basically, or also cells or body parts. So sample entities would be like tubulus, aspiratus, ambroid bodies, NK cells, and so on. And the classes in the same order would be tissue structure, organism, anatomical structure, cell, anatomical system, and so on. So a lot of complex terms and a structure we can extract from all this data, right? And now here we have a semi-long text. We can, instead of reading this, we can look straight at the visualization, right? The visualization and the prediction is always the same text, okay? So we can always look at the picture, unless you really want to see what's the confidence. Then you can pause the video or look at the notebook, okay? So we can see, patient skin is an organ, started peeling off after falling on his head. The head is an organism subdivision of the full body basically. And then we see, the the muscle organ is intact. And then we see turbinates are a multi-structure, cancer is a pathological formation, as well as cancerous and cancer, and the leg is again a subdivision, and so on. So we see lots of structure and information gained. And now a more simpler but yet very powerful domain is the bacterial species domain. It only has one label, species, but it understands all or most of the bacterial mentionings in the concrete medical terms. So if you say something like Spirocheta litoris seems to attack Neisseria wadsworthi, and I looked up, these are actual virus names or bacterial names, it detects that these two are species of bacteria. Perfect. And then you can easily scan for all relevant bacteria in your dataset, right? So all of these NER models, they give you basically the ability to scan and filter dozens or thousands of medical documents for relevant entities. And then another semi-similar domain is cellular molecular biology NER, which gives you, as the name suggests, genes, molecules, and cells of biology-related entities. So you can have something like human T-cell leukemia virus type something, or primary T LOPI something, or all these other terms, right? And then in the same order, the first term is the DNA, the second term is a cell line, RNA, and protein. And if this is, if all of these terms or terms like these appear in the free text, again, instead of reading all of this, we go straight to the visualization, but you already see the structure, right? This is just a blob of text, and now boom, we have a pretty pandas data frame. We see our text, protein, text responsive element is DNA, TRE is DNA, etc., etc. And in the visualization, we see it even nicer. Text is protein, these two are DNA entities, this is also DNA, text, again, a protein, JART is a protein, etc., right? So lots of structure, again, uncovered from our data. Next domain are the chemical genes and protein NERs. This is, again, slightly different from the previous ones. It can distinguish between chemical, gene Y, and gene N, basically. And a concrete example for this would be the terms, basically, keratinocyte growth factor and nitrogen. These, all of them are gene Ys, and nitrogen is a chemical. Together with NF kappa B are mitogens, right? And then we see the relevant types of genes from our data. On the other side, if you want super simple chemicals, nothing more than chemicals, you can just use the chemical compounds NER. It just detects chemicals and nothing else. And as you might see, some NERs might overlap, but again, it's always use the right tool at the right time for you the right problem. And so if you just want to get the chemicals and don't want to distinguish what the types are, you could say resveratrol and beta polyphenol can be a dangerous mix. And then you know these two are chemicals. Cool. And then on the other side, there are also chemicals used in drugs, or so-called drug chems. And you get it, by the way, always, right, you see always the spells. I didn't mention now all the spells, but it goes without saying there's always a different spell in each new domain, right? We need to update the spells. So for drug chemical, right, we just say med NER.drugs. And we say patient is treated with anthracylines and taxamis develop amnesia. And then we see these two are chemicals and they are related to a drug treatment. And then the next very, very powerful domain, which will come again later into play when we look at the relation extraction, is the posology. And posology is basically, if you don't know, the science of drug prescription and how to describe drugs and the dosaging of drugs. And so here we have basically a very long text with prescriptions, and the table you already see. Oh, by the way, and how do you get it? Again, med NER.posology, and you have entities like dosage, drug, duration, form, frequency, route, and strength. And now in the concrete visualization example, you can say patient is given Fragmin is the drug with a dosage of 5,000 with subconsciously as a route, daily as a frequency, Zendagen is a drug, and so on. And you can see already all the text, this unstructured data starts lighting up with all kinds of structures and patterns we can look for. And we will see how the relation extraction gets us even nicer patterns and information. But this is already very cool. Okay, so now, oops. We can also extract risk factors. And risk factors are basically entities like coronary artery disease, or smoker, or obese, or the family history related entities. So things that tell you how risky a patient is, or especially these things are relevant for insurance companies, and they tell you how risky is it to insure an obese smoker that has also diabetes. It's most likely riskier to insure this guy than a healthy guy. And as a concrete example, again we can say patient is obese and diagnosed with diabetes mellitus and has hypertension and hyperlipidemia, and he took glupirudin for 5 years. Now we know all the risk factors basically, or everything relevant for that. On the other side, if we now want cancer-related genetic entities, of which there are quite a lot, things like amino acid, anatomical structure, again a couple cell entities, but this time it's more granular, so you can get more precise with your analysis, which gives you more entities, which in some cases, again, you might want this granularity, sometimes it's not what you need. But again, you have lots of granular individual entities about multi-tissue structure, organ, organism, and so on. And in a concrete example, we can just say, have here a couple of proteins and a DNA. Cool. And then a very simple yet powerful NER is the disease NER, and it gives you basically all the diseases. It's just similar as the Shem drug NER. It just predicts one label, the disease label, and that's it. Already very powerful. So in this concrete example, you can say the cyst is developing rapidly, that's a disease, and death is imminent, another disease. So that's that. Cool. So the next domain is the medical problem, treatment, and test domain. These are basically 3 types of entities, as the name suggests: problems like bleeding from ear, tests like MRT scan, and treatment like amputation. This all is a treatment. And in a concrete example, you can see here, and again, how would you load this? You just say medner.healthcare, and you say a 28-year-old female with a history of diabetes and type 2 mellitus. These are all the problems, and is obese, etc. And a BMI is test basically, etc., etc., is vomiting. So lots of problems this lady has, and lots of treatments. We can see here at the end. She was on metformin, glycine, and all kinds of things. Cool. And then in the next domain we have the clinical admission domain. This domain gives us an overview of entities related to the admission of patients into a hospital or a clinic. So if the patient is admitted, there are things like the date, the time, problem, test, treatment, occurrence, and also the clinic he went to, and so on we want to extract. And in a simple example, we can say the patient presented, which is an occurrence, to the emergency room, in this case the location, last evening is the time. Cool. And then on the other side we also have genetic variants, which basically detects 3 types of medical entities: the DNA mutation, protein mutation, and SNP, which stands for single nucleotide polyphisms. And so I double-checked, I googled what are some, I actually took a text from a real medical text from an abstract and just made all of these shorter. And we have here, for example, we can see, the T10 something is a DNA mutation, the protein, the P something is a protein mutation, and we can extract all of these, and the RS3 and the RS8 something something, they are single nucleotide polyphisms. Okay, and you can extract all of this again with one line. You can get all of these entities and informations and all documents with this information from your database. Cool. So next domain is the clinical, is the protected healthcare information. So most hospitals or most healthcare providers need to follow some kind of data regulation and protect the data of their customers. And with the NER models we provide, you can give a model a long piece of text and find all the entities which are a entity that is protected healthcare information. So which would these be? So like the organization, doctor, username, profession, the location, the state, the patient, the zip, the phone number, etc. And here we see in the text this is critical information. This is the date, the doctor, that's critical information. This is a doctor, this is a medical record, this is a date, the patient, this is an age, etc, etc. And so we can later use this to actually, since now we know what pieces of text are protected healthcare information, we can later on just anonymize them or obfuscate them. Okay? Cool. And then next domain is the social determinants or demographic data NER, which basically lets you extract entities that are relevant for determining the social, not status, but the occurrences, or like the determinants basically, which kind of define the social status. So basically it's entities like age, diagnosis, dosage, drug, frequency, etc. And all of these are relevant to define what kind of healthcare services can be provided, or also relevant for analyzing your medical records. And so concrete example is you can get things like the 21-year-old patient, the male person, the congestion is a symptom name, tired or the nice is a negation, and so on. So lots of information there. Cool. And now we come to some of the very broad and powerful NER models. On the one side you have the general clinical NER, and as you can see, it can predict a lot of entities and almost anything that could occur in a clinic. And so here is a concrete example with a lot of text. Oops, now I just scrolled too fast. Yes, here we are. And here we see we can get things like what part of the text is the section header, the age, the race, when was he admitted, the clinical department, the test results, and so on. So a lot of high-level relevant clinical information. And on the other side, you can get also medical terms based on the mentioned data set, which are more on the medical side. And if you compare them, there's actually a lot of difference between the entities. And again, here we see just a couple, but there are a lot more you could get. And then now there are a couple of radiology NER models. There's on the one side a small radiology model, which gets you general entities like image test, image technique, or measurements, or body parts. And it's something like the direction or things that are found because of an MRT scan, and also the body parts basically. And there's an extended version of this, the so-called what we call Radiology VIP Greedy Bioboard, which has all of the previous entities plus some clinical entities. And then there's the even mightier, and what we call JSL v2, or just JSL, VIP, clinical RD, which comes with a lot more clinical entities. So it's basically a mashup between radiology entities and clinical entities, and a lot of entities. So lots of information you can extract from this. Cool. And then, oh yeah, here you see some of the radiology entities. Again, you can get things like body part, symptom, injury, and so on. And now we come to the assertion domain models and overview. So before we jump into the 2 or actually like 4 models we have, let's actually clarify what is assertion. What does that mean? So I have here 3 simple sentences. The first one is Billy hates having a headache. The other one is Billy has a headache. And the third one is Billy said his father has regular headaches. And so all these 3 entities, if you scan them with the NER, all 3 of them will have the headache entity. But only the second sentence, right? Billy has a headache. Only in that document there actually is a headache present in the patient. The other 2 are mentioning headaches, but there is nobody actually having any headache. And this is solved by the resolution algorithm or models. It basically predicts for every entity the class or status of the entity. And there could be multiple classes. In this scenario, we could just say he has, like present or not present, but there are more complex ones like possible, planned, someone else, past, and so on. And how would this be useful? Like a concrete use case would be, imagine you want to analyze the survival rate of heart attacks. Okay, and how would you do that? You have a database of 1 million clinical patient records and you apply NER, right? You say, hey, I apply the NER on the data, I get all the records with a headache. But then this problem I just mentioned will happen. You get everything that's talking about headache, even if a patient doesn't actually has one. And so what you would do to analyze that, or in our case I meant heart attack, to analyze all the patients who have a heart attack, actually have one, you get all the heart attack entities, and then you also put a filter condition basically and say each entity must also be asserted as present. And if it is absent or something else, we're not interested. Okay? So this is the rough overview for assertion. And the first domain, concretely for assertion, is radiology. So for radiology related entities, we can predict if something is confirmed, negative, or suspected. Or disconnected. It's fine. In this case, the radiology, so we have 3 sentences and it's visualized below here, and you see the visualizations are a bit different now. So I put in all the 3 sentences, and below the X-ray scan it tells me it's a test. And below that it gives me the asserted status that I just mentioned. So the X-ray scan shows a hypothetical problem in the lung. And the cancer problem is present though, what I mean. And the X-ray scan shows no sign of cancer in the lung. So that is absent, right, which makes sense. And the X-ray raises suspicion of possibility of cancer in the lung. So here we have the possible status, right? Now we say maybe, maybe not, right? So there are multiple ways of how you can use that to filter your data. On the other hand, you have the healthcare and clinical version of the assertion, which is extended by John Snow Labs data, and it basically asserts if the disease or problem is present, absent, possible, planned, with someone else, past, family, or hypothetical. So here are a couple of visualized examples. The patient diagnosed with cancer in 1999, so that's present. And then there's And then the other sentence says there's no sign of cancer, so that's absent. Right here we say no sign of cancer by the test. And then tests indicate patient might have cancer. Then we say, this one is possible and hypothetical. And then we say CT scan is planned for 1999. And then we say, this is a planned entity, right? And then we say the patient leg was amputated last year, so that's the past. And we can even say the patient's father has cancer. So this is then we say, this is not the patient, but the father or the family. And we can say cancer is still possible. So again, the possibility. And then the other one is the healthcare clinical one with a couple less entities, but it's basically the same, just without the family, and instead it's just someone else. So we just won't go into detail, but it's basically mostly the same. Cool. And then there's also the healthcare classical, which again is also almost the same, so we will not go into detail. It's again the same example and mostly the same entities. So that's why I mean you have two domains. Let's get back to overview. So quickly, you have two domains, basically radiology, and then three flavors of healthcare. Okay, and here you see the concrete entities and examples for them as well, if you want to take the time. Cool. And then next, after the assertion, the assertion, we can take a look at the identification really quickly. It's super easy. How would you do that? All you say is a record, so you give it some text data with PHI information, and then you see a record, and then date has been obfuscated, tests has been obfuscated, ID, the date, the clinical department, and so on. So it basically anonymizes the data for us. Perfect. Cool. Now we come to the next quite large domain and also quite complex. It is the one of the relation models. And first, maybe you can get again a quick glimpse of the relation models. We need though to understand what is a relationship, or how do the relationship extractor models actually work. What's the magic behind it? So most of the sentences we have, right, they have multiple entities. Okay, and each entity can have a certain relationship to every other entity in the data set. And what we can do is we can basically predict, is there a relationship or not? Either for the binary case, or we can also say there's a multi-class relationship, and then predict the case for that. And so a concrete example would be, let's say we want to analyze the survival rate of amputation procedures, but performed on the left hand. So how many people survive when you take off the left hand? How would you do that naively? You say, okay, I use the NER model and I scan for all the entities or all the sentences where we have the entity amputation, the entity left, which is a direction entity, and the entity hand, right? That's a body part. But then here's the problem, right? This, let's say we have this as a filter, right? We want amputation left and hand. But then if we have this sentence, the patient's left foot and his right hand were amputated. This sentence says left, foot and right, and hand. But the hand was not taken off, right? So this data sample, this record, would be a false record in our collection, right? Because we want to filter all the data for relevant records. So how can we fix this problem? We can say that there must be a relationship between the left foot and between the left and between the left and the hand entity, right? So the left is a direction entity and the hand is a body part entity, and they can be related. In this example, left and foot is related, but left and hand are not in relationship, right? And the entity right and hand are also not, they are in relationship, okay? And so we can limit the filter and say we only want the entities where there is a left entity, right, or literally left, and the hand entity. And they must be in relationship. If they are not, like in this example, we don't want to consider them. Okay, and so this relationship we can of course predict and detect with the body parts and direction relationship model. Because what is relevant to know is basically each relationship predictor takes, again, two entities, and they are usually of two types. In this case, they are always of type parts and direction, and so we predict that left and hand must be in a relationship. But then there's another edge case, which we will not get. Imagine now the sentence, the patient's left hand was saved, but the foot was amputated. So how do we fix that? What can we do? In that case, we can leverage the body parts and directions relationship extractor for, the body parts and procedures, right? So an amputation is a procedure type entity, and the hand is a body part, right? And we want to find a relationship that the procedure, which in this case is amputation, is performed on the left hand. And so we can, again, use two types of relationships now. We say we want only the hand and left. So first of all, a directional relationship between left and hand, and then also a applied, like a procedural relationship between the hand and the amputation. Right? If all of these conditions are met, then we can properly analyze the survival rate of amputations of the left hand. Okay, cool. And now I hope we have a rough idea of the relation extractors. Now we go over all of them, but quickly to get a high-level view again. You see the first ones we will cover, they are binary type of relationship, right? And either there is relationship or not. Like left and hand are related or not. Okay. Or a problem like pain in the ear is present or not. And then of course you can get adverse events, like an adverse event is caused by a drug or not. And then what follows after that are the multi-class relationship. For temporal you can have after, before, overlap. And for dates even more, and clinical problems have also a lot, and we will come to them right away now. So, what's the first one? The first one is dates and clinical entities. So for a date entity and a clinical type of entity, we can find out if or what is the relationship. So in this scenario, if it says 1, they are related, and so we say the patient developed cancer after a mercury poisoning in 95. And all of this has relationship 1 because it happened at the same time. But since 21, patient showed signs of leukemia. So this happened, is related with 21. But this is not related with the other ones, right? And how would you get this, by the way? Of course, all we keep doing now is, of course, we just say NLU.load. And the only thing we must specify now is the NER model in front. And then you define the relation model, because you always put the NER model in front because you need entities first, and then you can find the relationship. If there's no entity model, then you don't have nothing to find relationships of, right? Cool. And then the next domain is the body part and direction. We already mentioned that, so we go right to the visualization, right? And all you need to do is see is that you can say patient's left foot was amputated. So left and foot are related, right? This yes, this relationship between the direction is true. But in this case, the right foot and the right arm were saved. So in this case, this right entity refers to this foot, right? This is why we have here, maybe let me full screen this, as a 1. But this right does not refer to this right or this arm. And this is why there is a 0. Or this foot is not referring to this right. Or the foot is not related with that arm, right? So we know, there is no relationship. Cool. As I mentioned in the analytical problem, this is very useful. And then, of course, besides the directions, you can also see if there's a relationship between a body part and a problem. Let's say bleeding and the ear. Okay, or in this example, patient reported numbness in his left hand. Or you can say he also reported pain in the shoulder. And so the pain and the shoulder are related, and the numbness and the hand, but there is no pain in the hand, right? Cool. And then, so this is the problem, right? Problems are things like pain, bleeding, numbness, but on the other side, we also have things like procedures. Procedures are things like performing ultrasound, amputating a hand, performing heart surgery, and so on, right? Everything you perform on the patient, or a doctor does to the patient. And in this case, we can say the chest was scanned with a portable ultrasound, and an amputation was performed on the foot, right? So this is the procedure, and this is the body part. Or we can say a test was performed on the body part. Cool. And now to a slightly more complex domain. Or actually no, this is still binary. This is the adverse drug event. Domain is also quite simple. If we go to the, all you need, right, is just relation of other. And if we go to the visualization, we can see for the sentence, I've been taking Lipitor for 15 years and have experienced severe fatigue. So that is an adverse effect, something bad that happened because of Lipitor. And then he says, doctor moved me to Voltaren 2 months ago. So far, have only experienced cramps. So Voltaren and cramps are again also a related adverse effect. Perfect. And then on the other hand, you also have another binary relationship between phenotypes, phenotype abnormalities. So if something is broken with the human, basically, and genes or diseases. And so a concrete example is, you can say, she has retinal degeneration, which is a human phenotype, right? Or in this case, a problem with the human phenotype, and hearing loss, which is another phenotype, caused by a mutation in the G3PX2B, some gene, right? And then you see, this gene is related with the hearing loss, and this gene also causes the degeneration. But the HP entities are not related, right? Cool. And then we have the temporal events, which give us the relationship between clinical entities and time entities. And we can predict that cancer happens in 1991, or somebody was admitted after the cancer, or somebody was discharged before receiving some procedure. Right? And here we have a couple examples like cancer in 1991, or Mayo Clinic in 2020, and also discharge in 2021. Cool. And then next we have the dates and tests and results. In this case, it's all again a bit similar than the previous one, but we have slightly different relationships. On the one side, we can say something is a finding of something. For example, we can say on March 1995, an X-ray was applied, right? And because of the X-ray, we found the headache. Maybe let's look at this in the visualization right away. We see on 1995, there was an X-ray applied, and the tumor is the finding of this X-ray or this test, right? And after that, we have the clinical problem, treatment and test domain, which basically gives you dozens of, or not dozens, but a couple of relationships that can be between problem, test, and treatment. And we can go further down here where we see the example very clearly. So the first relationship is TRIP, which means that the problem has improved because of a medical cure. So you say the infection was resolved with antibiotic course, so it got better, right? On the other hand, you have the TRWP, patient's medical problem became worse because of treatment, so it worsened. So in this example, you say the tumor was growing despite the drain. And then you have the other relationships like a treatment caused the problem, like penicillin causes a rash, or you can say a treatment was administered for a problem, for example, dexaframine for narcolepsy, or the administration was voided because of a medical problem. For example, Rafalene was not given because of ulcers. And then on the other side, an angiogram revealed a partial effusion. This is a test has revealed a medical problem, so the RP relationship, and the CP says a test was performed to investigate a problem further, so X-ray for pneumonia, to investigate the pneumonia, and finally, if something is related to each other. So arthnopia presumed secondary in sepsis. Cool. And then, if you have a larger text, of course, this gets very structured, very fast. And if you have the time, take a closer look, please, later. But next, we take a closer look at the DDI domain of relationships. So, what is the relationship between one drug and another drug, or what is the interaction? And so there can be 5 types of interactions: advice, effect, int, mechanism, and force. And basically, advice means you advise to take something. Effect means something is affected by something else. Int means we already know that is established. Mechanism is a mechanism. And force is there's no interaction. And we can see aspirin should not be used in combination with paracetamol or antihypertensive drugs. Potentiate Xanax is an effect, or gabapentin is a mechanism on terbinafine, or avastin does not interact with chlorothalidone. Cool. And this is already how you get all the relations. There are a couple more though. So another very powerful one is a posology relationship I already mentioned. Right? We already can get posological entities, and now we can find the relationship. So if it's an adverse event, a dosage, a duration, a form, frequency, reason, route, or strength. And so more concretely, we can see here that oops, it's a bit tricky to read. The first one is dosage. So took 5 milligram of RXNORM is the dosage. Took aspirin daily for 2 weeks. That's the duration, right? And then relationship with this drug, right? And I took aspirin as tablets as a form. Aspirin usage is weekly, is a frequency. And then you can also say aspirin orally or strength drug. Like 2 milligrams of aspirin is the strength. Cool. And then I just want to show this is what can go wrong if you have too many relationships. You can end up with quite a messy plot like this. And I thought it looks pretty funny, so we can keep it in. But after that, there's one very huge domain left for us, and it's the chemical and proteins. And we then basically the Temporal paper and data set define 10 types of relationships between chemicals and proteins, which fall in the categories of part of, regulator, upregulator, downregulator, agonist, antagonist, modulator, and cofactor. And here you have a couple of examples for them. But yes, I leave it up to you to check them all, but because I think we are a bit low on time now, and you can have some fun going into some chemistry topics. But you have here a couple nice examples. And the last thing we should cover is just the data structure of what you actually get when you predict, right? What does the data structure of this pandas data frame look like when you predict on a relationship type model, right? That is what I didn't mention so far. And it's pretty simple though. You get one row per predicted relationship. So in this case, we have let's look at the body parts and direction, right? So you have patient's left foot was amputated, the right foot and the right arm were saved. So if you look in the relation column, this first of all tells you, is there a relation, yes or no? and between what? Entity 1, which is left, entity, and that's the class of this entity, and then entity 2, which is foot. And then we see left and foot have 1, so they're related. Ah, makes sense, right? Or right and foot have 1, they're related. But right and right have a 0, they're not, makes sense, not related. Right and arm, in this case, the arm, this right, the first right doesn't refer to that arm, but the other right has a 1, right? So now you know the rough data structure, basically. You have 1 row per relationship. And similarly, for the assertion, which I didn't mention, so I just mentioned it now briefly, you of course get 1 row per entity and predicted assertion, right? So if you have 10 entities here, cancer, cancer, scan, cancer, CT scan, you get for each entity here 1 row, and then the asserted status of it. And of course, always the confidences and all the additional data. Great. Okay. So now we covered all of the algorithms except the final one, and one of the most powerful ones, the resolution models. So what are actually resolution models? What can we do with them, and why are they powerful? Again, a simple example to show light why and how they are applied. Imagine, again, you have a simple string. Tesla is a great stock to invest in, and there's the entity Tesla, right? And we know this is a named entity. But now, look at these 3 strings. Tesla is a great stock to invest. Oops. Or you can say Tesla is a great stock, or Tesla Inc. is a great stock. All of these 3 entities are of type company, and they are referring to the same company, but they do not have the same form in our data. If we would do a group by, this wouldn't be grouped because it's not the same. And this is very bad for data analysis. And how we solve this is that we say, we give every company an ID, and let's say Tesla gets the ID 3. And so then what we can do is we give all of these entities to our resolution algorithm, and for each entity, it predicts the ID. And in this case, it would predict for all of these 3 mentionings of Tesla that it is of ID 3, right? Because it makes sense. So, and this of course is done with the resolution algorithm and is a very powerful way to analyze your data. And of course, in all the previous examples mentioned, it's written in the text, but I didn't mention it, you always should work on a resolution basis, right? Because you don't, since exactly this problem would occur, right? You should always, when possible, work on the resolved codes, because the string data can always have various forms and representations, and you want always a universal meaning or terminology defined. And so the medical world has a lot of terminologies defined. We can leverage, and JSL has prepared for you to resolve your entities. So what you can do is basically you can have tons of diseases or procedures and map them to international coding standards. Some of them, or the first one would be the ICD-10, the International Coding Standard from WHO for general diseases. And so you can map each disease to its ICD-10 CM code. Or there's also the ICD-10 PCS code for procedures, or the oncology version for ICD-0, or the HCC is for billable stuff, CPT is another procedure terminology, LOINC for general identifiers, HPO for the human phenotype ontology, UMLS for that standard, and SNOMED and RXNORM for the corresponding domains, and RXNORM of course for the drugs. And I'll show you how to use them. It's super easy. Again, all you need to know is just you put in the NER model and then the name of the resolver, and that's all you need to know. And then you predict with the model. And in this example, and again, you get 1 row per entity, and then you get an additional entity, right? You know, the first entity is tobacco, and it's of class smoking, and we have confidence. And then we have the sentence resolution, which resolves in the ICD-10 CM. This is defined with a normalized string as tobacco use. So it gets a normal version of the string and the code, which is Z202. And if you look it up in the database, it is actually the right one. It will show up as tobacco usage, and you can of course visualize this. And the visualization basically, again, adds another row below the entity class. You see the code and the normalized version. And we see hypertension has a code, chronic renal suffering has also a code. Cool. So ICD-CM, just as background knowledge, is basically diseases and problems, but ICD-10 PCS is for procedures. So for example, we can say the cast was removed from the face, and so the cast, like the medical cast, and that is a concrete procedure that has an ID and a code, as well as like a CT scan was performed, and that has also a scan and a normalized version. On the other side, for cancer or oncology based problems, there's a whole own terminology or coding standard, the ICD-O, which you can also use to get the oncological IDs, or the ICD-O IDs of oncological entities. Like mesothelioma is this here, and malignatis is that, and so on. And the HCC is used by doctors and insurance companies to define how much a treatment should be paid or reimbursed, right? It defines as a doctor how much can you get paid for something you performed on a patient. And it again defines, it is based on the ICD-10 CM codes and the PCS as well, and it defines for every procedure basically again code, and then from that you can derive pricing. And CPT is basically similar to ICD-10. It's basically more focused on procedure, services and diagnostics, and again gets to the codes and also the normalized version for everything. So an amputation is a procedure with ID 61, etc. and has this normalized version, or a heart transplant is also a procedure with this code, and left is the direction. Cool. And on the other side, you also have the LOINC, which is basically logical observation identifiers and names, and another coding system used for various entities, mostly for findings of test results. So if you have a test and you find something out, it's used for that, and also to basically label or code, define numbers or codes for the tests. And after that, we have HPO for the human phenotype ontology. So every phenotype of a human is labeled. For example, the disorders include cancer, bipolar, schizophrenia, and you see all of them start with HP, and they have the normalized HP meaning and correspond to that. And then finally, almost finally, we have the UMLS, which is a unified medical language system, another coding standard, applicable to a similar domain basically, so we can just use the same sentence and then get basically the different codes of the different terminology, since each domain speaks also its own language. We easily have here the UMLS codes, or you can also use the SNOMED CT version, so you get the SNOMED codes, which is also basically medical codes for procedures and problems. And there's on the one side the CT version, and again here's a big oh yeah, and SNOMED is actually an extension for the general clinical context and clinical terminologies, right? So for example, we can say a woman, like gender or infant, they are all mapped, or the clinic name, they are also mapped basically, which is not defined in SNOMED in the previous terminologies. And then there's the international version of SNOMED, which is basically just the international version of that, and the conditions, which is basically the SNOMED for conditions. And finally, we have the RXNORM, which gives you the normalized RXNORM version of the drug, and also the RX QI, so the identifier or the ID. And so here in the visualization, we can see he was seen with some service, She was discharged with 50 milligram. Atribogram is a drug with the ID, and at night is a frequency, etc., etc. So here you can really see all the power and all the knowledge you can extract with NLU and all of the healthcare models. I really again encourage you, go over all the tables which are at the very top or also at the beginning of every section. There you can have a really great overview of all the tools of Titans you can use to revolutionize the healthcare industry. So I hope you learned a lot so far or today. And this is basically the end of the presentation. So here are a couple more resources and articles for NLU. And here is the end of the presentation. So thank you very much for your attention. Feel free to email me or contact me on LinkedIn for any questions and feedback, and I love to reply to you. So thank you very much and goodbye.